So on yesterday, let's just do a wee bit of review. We started talking about all things that are matter and that there are 3 states of matter. Tell me the 3 states of matter.
Solid, gas, liquid.
Easy peasy. Now we have the periodic table, which I will not, as I said, make you reproduce. Jeanette.
Regarding that, okay, so the book has 118 elements, and on our part, 112.
So there are some that are hypothetical and there are some that are known not to exist. And so depending on what you're including in the number, that's why they vary. I am not going to ask you specifics to how many are hypothetical, how many, periodic table is how we catalog them. The most basic of knowledge. Does that answer your question? It will not be a test question. How many elements are there will not be a test question. 100%. All right, so we have our major elements. These are the 4 elements that are required for life as we know it on this planet. And when they start talking about finding habitable planets, I actually took a really neat course. There's a great, just for your own, just in case you have all this free time, there's a website called edX, where you can go through and take classes at all of the major universities on the planet. Yeah, for free. For free. It's called edX, EDX. And now you don't get college credit for it, obviously. But I've taken some fabulous classes just because I love to learn. And I took one through, what was that one through? I think that was either Columbia or Queensland University. I took a class on what makes a habitable planet and what do we as humans need to do to find it and how do we know. It was really cool. There was a lot more math on it than I was anticipating, but it's super cool, super neat. I've done a bunch of sociology classes because I find mentality fascinating, herd mentality. I've done some psych classes. I took some writing appreciation classes. I took a class on pandemics before there was a pandemic. It was pretty cool. So edX, literally any topic you could think of. I've taken classes through Harvard, Columbia, Brown. They're fabulous. So just a little merit for you. But one of the things that we are specifically looking for, and when we say habitable,
free, right?
And it's all free. It's all free. Now, if you want a certificate, then they charge you the certificate, but I did not need a certificate. I just have bragging rights that I was a student at Harvard. Hello, Harvard University graduate, technically. So what they're talking about is when they say habitable, they're talking about habitable for us. Habitable for us does not necessarily mean habitable for other beings. Just like here as a terrestrial mammal, which is us, we're habitable up here, but if we bring a fish up here, suddenly this environment is not habitable for them. For us, we need oxygen, carbon, hydrogen, and nitrogen. These are the 4 major elements. We talked a little bit about what they did yesterday. We discussed the minor elements. A lot of these are nutritional that we will be going into some pretty great detail next term in nutrition, like calcium and phosphorus. Potassium. Potassium is really important for nerve impulse function, so is sodium and chlorine, although we chemically alter chlorine to become chloride. And so a lot of these we're going to be talking about as far as their specific roles within the body physiologically. And then we discussed our trace elements. These are only needed in very, very small microscopic amounts. And you don't have to furiously write down this list. No worries. We are going to be discussing a lot of these again in nutrition because that's how we obtain all of these necessary nutrients. Of course, you don't have to ask. You can just go. We're going to be discussing specifically iron, copper, zinc, selenium, iodine, just to mention a few. and their role in the companion animal diet. All right, so now we're going to discuss the most basic molecular structure, the atom. The atom has three components. One has a positive charge, which would be,
Proton.
yeah, proton, positive. We have one that has a neutral charge,
Neutron.
the neutron, and then a negative charge, electron. Now, in the atom, generally, all three of these structures are equal. You have the same number of protons as neutrons as electrons. But what we then have is atoms that are looking to stabilize themselves. Perhaps they are on the search for an electron because they want to become satisfied. And so that would mean now that they have a different number of electrons than protons or neutrons. Well, that changes the overall charge of the atom. We'll talk about this in a little bit more detail. But for right now, our protons and our neutrons are found right here in the center. What is this center called? The nucleus. And we have our electrons that are in a shell or a cloud around the nucleus. And how the electrons behave is very specific and is the same regardless of the atom. The closest shell right here, oh, I guess I can do this from here because my poor Zoomers can't see what the heck I'm pointing at. My shell right here will contain 2. Then my second shell should contain 8. This one only contains 4. And so this is a great example of how do I need to be satisfied? Fill up the outer shell. Now, I am not going to have you reproduce the periodic table in any way, shape, or form. Promise, pinky swear. But there are some just general definitions that I would like you to know. For example, the atomic weight. The atomic weight is specific to protons and neutrons. Electrons do not contribute to the overall weight because they are so small and insignificant. They have no ability. It doesn't matter how many electrons I have, they don't have the ability to alter the weight. So the atomic weight is only referring to the weight of the protons and the neutrons. Any questions about that? Oh my goodness, was that a sneeze?
I don't like sneezing in my mask, so.
No, here's the, well, and I recognize it because I am an inside sneezer. I hold them in, but it's something that I've had to train myself to do because I was a surgical assistant. So most of my job during the day was spent in surgery. Well, number one, it's disgusting if you sneeze all inside your mask. But number two, even if I'm in a superficial procedure, we don't even have to wear a mask. I'm not going to be like, and like blow bacteria all throughout the entire room, potentially contaminating my patient. So all of you that get into surgery are going to have to teach yourself to sneeze like that. It's terrible for you. Blow out your eardrums. But yeah. Anyway, sorry. It was adorable, and I was excited to see.
Like a man sneeze.
I was excited to see someone that sneezed like me. It drives my SO crazy when I do it. So our atomic weight, protons, neutrons, electrons do not contribute. And then of course we just discussed the charges. Electrons are negative, protons are positive, neutrons are neutral. Pretty self-explanatory so far. Is everybody on the bus? This should be kind of reviewy for a little part. Maybe not the most part, but for a little part. So electrons. These are teeny tiny particles that are constantly in motion. They can be associated with the atom, but they can also exist by themselves as free electrons. Free electrons are what we scoop up when we're moving through space. This entire room is filled with free electrons. And depending on how excited and happy those electrons are, determines how easily is it for them to stick to you. I think of the electrons like the little, I don't know what you all call them, the sticker burrs. You know when you walk through the grass and you come out and you have all those little burrs on your pants? Little stick, what do you call them? Are they sticker burrs? Yeah, we just call them sticker burrs.
I call them hitchhikers.
Hitchhikers, oh, I like that, hitchhikers. That's exactly what's happening, obviously, on a much larger scale. But for example, who gets electrified in the winter? Anybody? I can't be the only one. The minute that the air gets dry, oh Lord, during the freeze, holy crap, G. I was unable to touch literally anything because the air was so dry. And what happens is the electrons got excited. And for some reason, it's only some of us, other people don't have an issue with this. But when the electrons get super excited, and I'm even just walking through, just normally, not dragging my feet, not doing anything, they are sticking to me. And then the second that I would touch the doorknob, or I would literally touch anything, I'm getting a horrible, horrible shock because I'm discharging that electrical charge. Oh gosh. There were times I would have to use a pencil to touch my computer because every time I touched my computer, a literal spark would come out of my finger.
I guess I don't know, she doesn't like get me sometimes because like I would just like grab it and like I would shock her.
Oh my gosh. I don't have one. 99.9% of the time I have a dryer sheet in my pocket. It'll touch it. And what does dryer sheet relieve? Static electricity. Well, I'm building up electricity, forming a static charge, discharging it. So I keep a dryer sheet in my pocket and I rub my hands on it before I touch it.
And it smells good.
Do what, Charles?
He said it helps with the static electricity and it smells good.
And it smells nice, yes, absolutely. I almost always have one. So these electrons, they can accumulate and they're going to orbit. Remember we said yesterday, they don't orbit in a planetary manner. They're not like the planet rotating around the sun. They're in a cloud. And this cloud, you could have some gathering more on one side than another, which could cause part of the atom to become a little bit more negative and a little bit more positive. We didn't alter the number of electrons, we just changed where they were. Electrons having a negative charge, if I've got a whole lot of negative electrons up here, that area is going to be more negative. And if I don't have any negative electrons, this area is going to be more positive in comparison. That's going to be important when we start talking about hydrogen bonds, is the difference in the charges in different areas of the atom. That's it. That's all we need to know about electrons. Here's just some pictures. It's really hard to try and get you a 3D visual of an atom. It don't really have an atomic electron microscope or anything like that. You get the idea.
When I was in like chemistry, they actually told us that that doesn't exist. Like
Well,
an actual like diagram for like an atom,
it doesn't. It does not. It is a hypothetical blown up to give you a visual representation. All right, so we know the atomic weight was determined by what?
Protons, neutrons.
Protons and neutrons. The atomic number is designated by protons only. So the number of protons is what determines the element's atomic number. That's a definition. So go ahead and put a little star beside it. So we know that our atoms typically will have the same number of protons, neutrons, and electrons. And an atom's job, an atom's life goal is to get the electron shells full. However, that has to happen. Now, atoms tend to be a little bit lazy, and they're going to take the path of least resistance. So if their outermost shell only has a single electron, is it easier to go out and find 7 other electrons? Or is it easier just to ping off that one? Just easier to ping off that one. Same thing, let's say if I have an atom that has 7 electrons already in the outermost shell. Is it easier to ping off those 7, or is it easier to go find one to satisfy? Find one. So if I gain or lose, if I ping off or collect an electron, that changes my charge, doesn't it? Because if I take in more negative electrons, what happens to my charge? It changes to what?
Negative.
In negative. Yeah, if I have more negative electrons, my charge becomes negative. If I get rid of the negative, how do I feel?
Positive.
I feel positive. So we get rid of the negative feelings, we feel positive. I take on the negative feelings, I feel negative. That's how we determine the charges. But the other thing that's going to come into play when we are looking at bonds, what do we know about opposites? They attract. So if I have an atom that has lost an electron and has become more positive, and I have an atom that has hoarded that electron and become more negative, I now have a positive, I now have a negative. They're going to be very attracted to each other, and they're going to hold hands. And this type of bond, this holding hand bond, not super strong, is called an ionic bond. Again, don't write that down right now. It's just so you've heard it before we get to it. If I gain or lose an electron, I am now called an ion.
What's the bottom red one?
I have not gotten there yet, but it is isotopes.
Isotope?
Yeah, I have not discussed that yet. So we have gain or lost an electron is an ion. But we also have something called an isotope. I-S-O-T-O-P-E. Isotope. And what this is where I have a different number of neutrons than protons. That does not really do anything to the charge. The part that controls the charge primarily is the electron. Our protons and neutrons, however, if I have a different number of each of those, it's called an isotope. I really can't go around and collect more neutrons or collect more protons. Stuff that's in the nucleus is pretty much trapped. And it's really hard to manipulate anything in the nucleus. So if I have a different number, those are isotopes. It also always reminds, isotope always for some reason reminds me of isotoner gloves. You have no idea what those are. But up in Canada, that was a very, very popular brand of gloves. And they were very warm, but they were also very thin, like they showed you could pick up a quarter off the floor with the gloves on. Oh, isotoner. I don't know why I keep speaking of that. So here I just have some pictures kind of showing our 4 major elements. Here I've got a little hydrogen. And he's only got one little electron in his innermost shell. Well, technically, he's only got one shell. The first shell, I want to have 2 to be satisfied. Can I get rid of this one? Why can I not just get rid of this one and satisfy the shell? Because then the shell is gone. Is it an atom if there are no electrons? It is not. It has to have all 3 components to be an atom. So what is hydrogen's only option?
Combine.
We either need to go collect one or we need to share one. Either way. But once I get the 2 in the shell. Hi, Mr. Eric.
Morning, I'm sorry to interrupt. Giselle?
So if I have 2, and it doesn't matter if I've grabbed one or if I'm sharing one, I have now added an electron and the charge has become negative. Yeah, if I hold on to negative stuff, I become negative. Now, if I have had one donated from somebody, that is what makes an ion. Ion, we gain or we lose an electron. Here we have carbon. Carbon's innermost shell is satisfied. Here we have 4, and we want 8. Now this is where carbon is kind of an interesting element because it takes the same amount of energy to go grab 4 as it does to lose 4. And so he really has the plethora of worldly options open to his platter. Here we have nitrogen, again, we've satisfied. Here we have our 2, and here we have 1, 2, 3, 4, 5. So what is going to be easier for nitrogen to do? Lose 5 or gain 3? Gain 3. We're usually going to take the path of least resistance. And then, of course, we have oxygen that has 2, 4, 6. What do I need to do to satisfy?
Gain 2.
Gain 2. This is H2O. Because what I can do, oh, we got excited. So I have, oops, I'm not even gonna draw it there. So I've got my little hydrogen, and hydrogen wanted what? He wanted 1. But do you see if I draw a hydrogen right here? Here's 1, and then hydrogen had 1, and now we can share. And down here, here's 1, hydrogen has 1, we can share. 1, 2, 3, 4, 5, 6, 7, 8. Oxygen is satisfied and happy. 1, 2, 1, 2. Hydrogen is satisfied and happy. Sharing is caring. Caring is covalent. It works. It works. It's not stupid. It works. We just made our first covalent bond, you guys.
Have a party.
I know.
Have ribs and listen to Aerosmith.
Oh, heck yeah. I'm going to be having me some barbecue this weekend. What? My significant other has a hankering, so he's decided he's going to make all of the barbecue.
I'm sorry, why wouldn't that be ionic? Could you give an example of an ionic bond?
Absolutely, I can. Let me jump forward for just a second. Bam. Look who's ahead of the curve. So here I have, I'll go back to the isotope, don't panic. Right here I have Na. Someone tell me what this is. Sodium. It's natrium is the technical term. Na is sodium. Sodium is a really kind of interesting little atom. I have my innermost shell. One, 2, satisfied. My second shell, 1, 2, 3, 4, 5, 6, 7, 8, satisfied. His outermost shell has one sad, pitiful, lonely electron. And what do we know? Path of least resistance. Pew! So what sodium's gonna do is he's gonna run around saying, hey, like a scalper. Anybody here need an electron? Anybody want an electron? It just so happens that the guy that most commonly joins up with sodium is like, yeah, my brother, I want an electron, please. Because chloride has 7 in his outermost shell. And so when sodium's like, hey, you want an electron? You want an electron? Chloride's like, ooh, I want one. And so sodium pings it off. Chloride grabs it, puts it on. The outermost shell of sodium is now satisfied. And the outermost shell of chloride is now, but sodium lost an electron. We got rid of something negative. What has happened to its charge? It's become more positive. Chloride has picked up something negative. What has happened to his charge? It's become negative. We have gained and we have lost an electron. Both of these are now referred to as an ion. All ion means is that we now know we've gained or lost an electron. But in this specific example with sodium, lost one. Chloride, grabbed one. We now know that one is more positive and one is more negative. And what do we know about that? Opposites attract. And we now have them in almost like an electrostatic, pretty weak bond. It's a pretty weak bond. But they're going to be excited and attracted to each other. That type of bond between ions is called an ionic bond. So that is an example of an ion. Is everybody on the bus so far?
So both chlorine and sodium would be considered ions in that case?
Yep. And then we would go further to distinguish which one is the positive ion and which one is the negative ion. Because the word ion simply means gained or lost. It doesn't tell us which one gained and which one lost. That's when we go further and we look at the charges. Going back for just a second, here we have our isotopes. Isotope was by definition what is happening to our atom. We have a different number of protons than neutrons. That's it. And some of these isotopes, depending on how big the difference is, can become pretty unstable.
So they're not identical, then they're unstable.
Yeah, they can be. Not necessarily, but they can be. So yeah, isotope, we just have 2 different numbers, different number of neutrons, different number of protons, and ideally we would want them to be similar. The kind of interesting thing, and the reason why I use carbon here, because remember carbon is a really just slippery, interesting element. Have you guys heard of the term carbon dating? Like I find the fossil, and I go to Blathers in my museum, Okay, like 3 of you got that.
Yeah.
Yeah, you got me.
I played some GameCube, so like.
I am just, yeah, I'm having so much fun with this game. So I go to Blathers and he carbon dates. Okay, he doesn't, but I'm giving you the example. You go to the museum and they carbon date it, and they're able to tell you this fossil is 35 million years old. How do they know? Well, because these are isotopes, and that's what they are looking for, depending on the difference of the neutrons and protons, nothing is forever, and these will begin to degrade. We are all, everything that lives on this planet is a carbon-based being. So I can take the carbon in that fossil. Just like life is fatal, you guys. None of us are getting out of this one alive. Like it is, life is fatal. We are all going to die at some point. And 10,000 years into the future, they happen upon our bones, and they're going to look at the carbon that the bones were created, carbon backbone. And they're going to look at the degradation, meaning how much has this carbon decayed? And knowing what's called the rate of decay, how, essentially, if you want to think about it, like the carbon starts to rot. How long does it take to get to this level of rot? No different than a dead body. I'm all into the true crime. There are studies done where I can go and see a dead body, and based on the rate of decay, determine how long have they been dead. That's literally what we're doing here with these isotopes. We are looking at these specific carbon isotopes. How far have they decayed? It is in fact called the rate of decay. And determine how old is the carbon, which then in turn tells us how old is the structure. So there, a little real world science application for you.
Ms. Huff,
Gosh, I got right
so
ahead.
can an isotope ever have the same, like go back to having the same number of protons and neutrons?
No. For what we want now, if I were to do like a beautiful mind kind of thing, it's all theoretical. For what we want in this very beginner lesson, my answer to you is no. Here we have the radioactive, the rate of decay that I literally just explained. I did not realize I had a whole PowerPoint slide over this. I get excited and I forget. So that is the disintegration. As these carbon atoms also disintegrate, they release radioactive material. And then again, in turn, we can measure how much have they lost, and that will tell us how can we date these fossils, how old are these fossils. So this is just mainly interest science and a real world application for an isotope. It's pretty exciting. I always thought it would be really cool to be like an archaeologist. No.
I have a friend right now who's doing her undergrad in archaeology in Idaho, and it's boring.
I always thought it would be like, Indiana Jones, Tomb Raider, you're in this dusty, you have the scarf around your face and there's a sandstorm and you're walking and trudging and the sand blows away and you're like, what is that? And you've just discovered an entire underground old civilization. You get your picture on the cover of Rolling Stone magazine, not architectural. The whatever publication they read. No. It's basically like Dead Thing Librarian. You work in a static, sterile room and you just catalog crap.
And a lot of archaeology modernly is learning about how archaeology in the 40s and 50s was just so corrupt.
Oh my God, they stole everything that wasn't nailed down.
And we have no record of any of it.
No, they stole everything. They're like, oh my God, look, something shiny, put it in your pocket.
Yeah, we're
Don't
missing
put that on the list, Craig. Don't put that on the list.
archaeology. We're missing huge swaths of information.
Damn it, Craig. I said don't put it on the list.
We're missing huge swaths of human history because of
They stole it and sold it. Yeah, got
A
it.
lot of it was melted down, like
Oh, yeah.
precious metals and stuff, just melted down,
Oh,
and we'll never ever
yeah.
know.
No. But I always thought it would be super cool, but no, hard no.
Wait.
No worries. No worries. Heck yeah, Kuna Matata. Yeah, I was gonna take an archaeology class through edX, because before I started my bachelor's degree, that's kind of what I would do, is I would take these classes. And yeah, I got like a week into it and I'm like, nope, this is not for me.
I wanted to do anthropology,
Oh.
which is slightly more interesting.
It is slightly, it's got more of the sociology and socioeconomic backgrounds behind it. I find that fascinating.
I majored in anthropology, and honestly, I think it's pretty great. So if you have any questions, I could talk about it with you literally all day.
Yes. We will schedule some time for that because I find it fascinating. I have been to Chichen Itza. Is that how you say it? Chichen Itza. It is Chichen Itza? Oh, it's so exciting. And I went back in the day where you could actually tour around. Woo! So exciting to think that the people up there, and you can just like visually imagine them dancing and partying and doing all of their things around you. All right, so this is a review slide, our electron shell. We've already talked about this. The electron shell is where the electrons gather. They are, again, not moving in a planetary roll. They're in a cloud, and the cloud can gather more to one side than the other. For example, you know what? I'll give you the example here in a minute. I'm getting excited again, and I tend to just trip over myself. So lower energy electrons are going to be closer to the nucleus. Here's how I think about that. The nucleus is like the house. And when I'm feeling super low energy, how far away do I want to go from my house? Not far. So our lower energy electrons stay pretty close to the nucleus. And as you see the electrons in the outer and outer and outer shells, the more energetic electrons are further away from the nucleus. Just like, although I'm not very energetic these days, to tell you quite frankly the truth, I'm very happy to just sit and watch The Office and Netflix in my home. But back in my younger days, oh my gosh, my sister and I would go to San Antonio for dinner. We'd drive 3 hours, go just have dinner, and then drive back. It was so fun. You know, one of those things, went to California, Los Angeles. I have some family that lives out in California. We drove to Tijuana for dinner. We went to a whole other country just to have some good margaritas. We were all sitting there, me and my friends and my buddies and my family, and we're like, man, I would really go for a great, you know, nice margarita right now. And we were kidding. We're like, hey, Tijuana is like 3 hours away. Let's go to Tijuana. Okay. Are we doing this? Yep. But thankfully, this was way back when you could get across the border with your driver's license. You didn't need your passport. Thank God, because I don't have an American passport. I did not have my Canadian one with me, or my green card. So I almost got stuck in Mexico forever.
They would have loved you.
I know, right? If I have my electron shell already satisfied, I have the exact number of electrons that I need. I am satisfied with my life. I don't need to go find a partner. I don't need to get rid of a partner. I don't need to find an electron, get rid of an electron. The term for that is called inert, meaning they're just satisfied. They're not out seeking. There are two elements that are what we call inert, meaning their outermost electron shell is already full and satisfied. Helium and neon. They don't need to find anything. They don't need to give anything away. But the other thing is that means that their charge is neutral. So it is very difficult for them to bond with other elements.
That's I-N-E-R-T.
I-N-E-R-T, inert. And I just, the sound of the word kind of makes it sound like what it means. Like, if I say to you guys, I'm feeling really inert right now. It means I'm not happy, I'm not sad, I'm not positive, but I'm not negative. I'm just kind of meh. That's my feeling when I'm inert is just meh. So there's our shells, again, review slide. I put in a lot of these review slides because the more you hear this stuff, the better your pathways are going to get paved. So our first shell contains 2, second shell contains 8, third shell 8, fourth shell 8. That's as far as we're going to go. We're not going to the astronomical shells. 2 and then 8 going forward. So when I have these atoms bonding together, they make molecules. If I have 2 or more atoms of the same element, that's called a molecule of the element. Well, it's kind of a duh, really. I call it a no duh. If I have 2 elements that are the same that bond together, anytime I have atoms bonding together, we make an element, or not an element, a molecule. And so if I have the same elements making a molecule, that would be a molecule of those elements. How do we get these atoms to stick together? Bonds, and we've already talked about these. This is super not shocking information. I have ionic bonds where I have a positive and negative, they attract. I have covalent bonds. Tell me our little statement that we remind ourselves what covalents are. Sharing is caring. Caring is covalent. This is where they're sharing. And I just showed you an example of that with the hydrogen and the oxygen. And then if I have 2 or more different elements, that is known as a compound. In fact, we do that a lot with pharmacology, with drugs. We have what are called compounding pharmacies. So let's say we do this a lot in veterinary medicine. You may have a child or even yourself. You're on 2 different medications. And these 2 medications enhance the action of both. And so instead of taking 2 medications, I can bond them together as a compound and take it as an administrative, or administer it as a single dose, but have both included. It's called a compound. 2 different things coming together as one. Think of like a cult. Jonestown. No, it was Flavor Aid. It was not Kool-Aid, it was Flavor Aid. I correct you on that. I am the expert. Any of them. They live on a what? Compound. A bunch of different entities coming together for the greater good in their minds. Time flies when we're having fun, you guys. We're going to pick it up here on tomorrow. then continue discussing bonds and what they do and how we need them. I'll leave that up for you. Any comments, questions, concerns? All right, let me just pause this recording as we are